Okay, let's continue. So in the last lecture, I explained at the quotient level the geometry of this Lagrangian submanifold for the period map, and we discovered basically the generating function to be of this type, which somehow, in this example, is split into two parts. One of them is about this intersection theory, basically, imperial gravity. And the other part is the geometry of the Calabi-Yau manifold. That's split. And this is the essence about in the B model. It's localized to constant map, and that's the reason. And now I want to explain how to start from here, how to obtain the corresponding invariance. And in particular, I want to explain its relationship with the very classical construction of so-called primitive form, which leads to so-called Frobenius manifold. Okay, so now here's the picture for at the quotient level. And I mentioned like this period map interturns the two Lie structure, so it can pass to cohomology. So pass to cohomology. Now left-hand side, the corresponding Maury-Cardan equation on the left-hand side is given by this is kind of modular space. And I forgot what kind of notation I used before, but let me use this one at this moment. That all of the mu's Q mu so if you pass to cohomology, left-hand side, you got this modular space. So Q cohomology. So not only Q cohomology. So this is like a. Okay, let me be more precise. I mentioned that this is a map. It's an L infinity morphism between two DGLA. So here you have the Q and this bracket. And here, it linearizes everything to Q. So because this is like L infinity morphism, it maps the solution of Maury-Cardan equation, Maury-Cardan functor to the Maury-Cardan functor here. Passing to Maury-Cardan functor is what I mean by passing to cohomology. On the right-hand side, it really literally passes to the Q cohomology. On the left-hand side, it leads to solution of Maury-Cardan up to gauge. Maybe more precise is to pass to Maury-Cardan functor. Add a little bit more precise notion. So the left-hand side is this one. Right-hand side is basically Q cohomology. So you obtain the period map from this modular space, formally embedded into this cohomology. And we called this extended period map before. And also, like the sympathetic pairing is Q compatible. So
the left side is still infinite dimensional.
Infinite dimensional, yes, yeah. So it's really at the formal level, yeah. It's really infinite dimensional space, both left and both right. This is infinite dimensional. This half is infinite dimensional. Yeah, it's very infinite. But this infinite time, this is infinite dimensional. This infinite come from the t parameter. Yeah. So not from this x. Yeah. Okay. So now we know like Q is compatible with the sympathetic pairing. So basically, this pairing induces the pairing, sympathetic pairing on the cohomology. So of the same degree, like it's a 6 minus 2D symplectic. And now we basically want to do the same story at the cohomology level. And now you select S plus is the subcomplex. This is a sub-cochain complex. And if you pass to cohomology, you basically find isotropic subspace of this guy. This is isotropic subspace. So we almost get the same picture, almost. However, to compare with the story at the cochain level, it's not hard to imagine, like, again, this is a nonlinear object here. We want to write some kind of generating function at the cohomology level, describing this moduli space.
Can you define this cohomology on the right-hand side? Besides the vector space, what other structure? Is it LPP or what structure?
This one?
Yeah.
The linear space. The only symplectic space.
That's it.
That's it.
No.
Just symplectic. Yeah, just symplectic. This is a Lagrange subspace, isotropic. It's infinite dimensional. This is a nonlinear subspace, manifold. Yeah. I want to write the corresponding generating function for this pyramid. Now, the point is the following: like at the cochain level, there's a natural splitting at the cochain level, so you can just write this one as a cotangent bundle of this one, and blah blah blah. And here we don't have this choice, basically. However, so if you look at the negative part, this Q operation doesn't preserve this negative part. So this one is not a subcomplex. So you cannot just directly take the cohomology of this S minus to get a splitting at the cohomology level. There's no such thing. And then this one requires additional data if you really want to compute invariance. So just let me mention like this decomposition. This object does not pass to the cohomology level. Does not pass. Yeah, doesn't work. So let's define a new object, a new data to indicate such a splitting by hand. And we call it opted filtration. For this space, this entire space, is a choice of linear isotropic subspace. And such that first we got an isotropic splitting. Second, this one is preserved by T inverse. It really points to the negative order. So this means like if you multiply T inverse, it's map it to itself. That's the data we're going to use.
Isotropic splitting means that this L goes L and this cohomology of S plus.
So if you just compute the pairing of these two is 0. So the non-trivial pairing come from, in this sympathetic pairing, come from the pairing between this part and this part. So this is already isotropic subspace. This is also isotropic subspace. They do of each other. Yeah. This is just like in sympathetic geometry. Like this is a position, this is a momentum. They opted. I have to make a choice. Now,
if you have some structure do not descend to cohomology, you descend to some infinity structure. You have an infinity word.
Yes, I mean this is exactly the point. It's like the reason it just doesn't descend is about the Q. Yeah.
So you have supposed to capture infinity.
That infinity Q is precisely the action function I naught. I explained that point. It's really the way you pass to exactly. Then it's another way to explain where this I naught, the classical B0 action come from. I'll explain that next time. So because that's also important to understand what's the quantum case. In quantum case, do the same story. You just replace the simple structure by the standard Y algebra, and then again the homotopy transfer of this Q leads to the quantum mass equation. Yeah, it's a universal process. Tomorrow we have okay. Make sure. Okay, yeah. So now let me explain a little bit about this optic filtration because it's going to play a very important role. And a choice of this optic filtration and give a way to split the natural projection. Split. So originally, we have this cohomology of this X, and then sorry, this is about the plus part. And this one naturally mapped to quotient. And since we work with like compact Calabi-Yau, and we have this kind of Hodge drum degeneration, you look at this quotient. I mean, the Q looks like a d bar plus t del, and if you mod out t, this basically calculates the d bar cohomology. So this is isomorphic to the d bar cohomology. This requires a little bit of degeneration. We'll also explain this degeneration next in later examples when we discuss, for example, Lambda-Ginsburg or things like that, become highly non-trivial. Then this choice of this L give a splitting of this map. And how this works? This basically just by choosing the basis of element here, which maps isomorphically to this guy. So by the natural isomorphism, let's call this one. Let me first write it down. you observe like the split is like this one to the, you can think about this one as like a non-negative orders in T. This looks like a negative orders in T, so you preserve by this operation. Then you can somehow look at how they build up from each other by choosing the basis, like look at this intersection. So this looks like picking up the order, zeroth order in T. And let's call this one a basis BL, related to this choice. And this maps isomorphically to this quotient. Which is identified with this cohomology. So a choice of this Lagrangian basically gives us a way to split this quotient map. And you think about this one as like order T to the zeroth order, and then with this choice, it can write everything by let's write. I want to simplify the notation, so let's write. Let us denote. Let's call this one H to be this whole cohomology, and let's call this H plus to be this guy. And then with this choice, you can write basically this H to be in terms of this basis. You can write it as follows. And H plus, oh sorry, this is Lorentz in T. And this one can be written as non-negative orders, and this L can be written as the negative orders. So once you choose a basis like that, you can write everything in such a way. You can identify. Now we can write down the corresponding geometry of the Lagrangian at the cohomology level. Now I can erase this part. So if you look at the picture and the formula there, you see like we can identify the whole cohomology under the choice of this Lagrangian as the cohomology of the plus part under the splitting. And then we can draw the picture.
Second, you mean that if you have a subspace called BL,
yes,
if you isomorphism, that becomes L.
The choice of this BL, the same thing as the choice of this L. Yeah.
Yeah, so you just choose a subspace.
Choose a subspace, yeah. Then once you choose a subspace, basically you can write everything like just what we did before. Yeah.
There's no assumption of BL. You just get this so that you should drag that.
The BL has the property, so it's like it has come from these two. These two will imply the following. This will imply that by the condition of L, choice of L, probably remark. If you compute the pairing, so this implies it's basically a pairing on. I will mention this one later, but so how can I say? This is a really it really requires a high-risk pairing, but let me say. So let me just say that these two stuff and are simply dual of each other. Conjugate. This is a consequence of the property.
So if you have such space, then you recover L.
Yes, you can just write L like that. Yeah, and this is also preserved by T inverse. Yeah, and you see because of this property, this L is isotropic. Yeah, the same data. Yeah.
就是write down as a topic.
Yeah. Now, then you can see once you have that property, and you can identify this cohomology, the big space, as the cotangent bundle, and you have applied this to the moduli space. Anyway. There are many else, a little bit confusing. So this is my image of the period map. Okay, then you can write the image of this moduli space as the graph of something. This guy actually depends on the choice of splitting. So this one is a function on this cohomology on H plus, which can be identified by this choice, like the cohomology of this polyvector field with D bar. By the way, this cohomology is called a B-model state space. Say it again. Yeah. So this is this so-called genus zero B-model invariance. I want to explain a little bit about this data. Later, I will tell you like more structures about this invariance. Probably you know, like in the general story is like this will give you some kind of Fourier manifold and things like that. It comes naturally when we understand like good enough about this geometry. But let me say a few more words about it. So. Yeah, this step is the step it took another year to understand how this one goes. But let me just tell you the answer. So let's consider the geometric meaning of this splitting. So geometry of the opposite filtration. So one way to understand this one is the following. So let's do the following identification. Define, let's call this one gamma omega is mapped to polyvector field by contracting with the volume form to differential forms. Which maps t to the k mu to t to the k plus I minus 1 mu contract with the Calabi volume form. So here is like poly I something. But the map goes as follows. You send poly ij to a differential form, which contract the differential poly vector field with the volume form to get a different form, and they shift the t variable by this weight. So basically shift by t I minus 1. This is a unique shifting which allows you to identify, for example, poly 1, 1. That is that's the place where you describe the moduli space to like element here, the cohomology. And also intertwines the operator Q. To the standard Durham differential. And because of the shifting by order t, this operation becomes the standard Durham differential. Then what's happening is the following. It's almost a unique one you can write down. Then you can observe. We have this is my full space. Now you look at the corresponding subcomplex by the S plus. So if you look at the image of S plus, and if you do a quick calculation, you find the following: like product of this object T to the D minus P minus 1 Fp omega. So here, this one is about Hodge filtration. It's sort of clear, or it should be easy to calculate. We can do a quick calculation. So it's like I think this is very important. I want to really convince you this is the correct object. So for example, if you calculate, say T to the K, say poly I something. For example, you want to calculate T has to be non-negative order, and under this map, it becomes like a T K plus I minus 1 omega D minus I something. And if you think about it as like let's call this one P. Call this one this object, and so let's call P to be D minus I minus K. And this becomes T, so this should be D minus P minus 1. And this becomes D minus I is the K plus K, P plus K. And K has to be non-negative order, and then this if you sum over order like non-negative order in K, you just get this object. So that's a quick calculation to see what's happening. Okay. So in particular, this one says the following. So if you pass this one to let's look at the, because S plus is you can multiply by T and look at the T quotient. So this gamma omega, if you look at how this map to S plus, quotient by T S plus, and look at the right hand side, you find map to isomorphically T to D minus T minus 1, the graded piece of the differential form. This graded piece is about the Hodge filtration. And which intertrains the d-bar operator here with now the d-bar operator here for this graded piece. And then what the splitting is sort of see here is like this L. Basically, it's a splitting of the Hodge filtration because you split the quotient map, which relate about this Hodge filtration. So this L is really a splitting of the Hodge filtration. At the co-module level, and there's a bunch of different ways that you can do this the splitting. like a standard way you can do some kind of a complex conjugate splitting. That's the way you decompose like a differential form into PQ type. This is called a harmonic splitting. It's harmonic splitting. Where it decomposes Hn to be P plus Q equals N PQ. But I mentioned like if you want to really compute invariance, you need a choice of a splitting. And this harmonic splitting is very natural, but it doesn't lead to the correct B-model invariance. The correct splitting comes from the second one. So around the large complex limit, there's a maximal unipotent data where you have a monodromy, and this monodromy gives you a splitting. This is also there's only a splitting which is close enough to this larger complex limit point. And if you calculate invariance under this splitting, it's the one you got this mirror to Gaussian invariance. But then there are actually many other splittings on the modular space in the B model. If you say around this Gapner point, you want to get this monodromy associated to singularity, you have a different monodromy splitting. That gives you the mirror to this is, for example, FJW theory, things like that.
But the other has also enough monodromy to split it?
Yes.
Canonically.
At the singular, yeah, Gapner point, yeah. When it's very singular. So it's like the arising from the singularity, yeah.
But this is like other singularity, like a non-equal singularity.
Not enough, yeah, you're right. Okay. So the last remark I want to mention is to compare a little bit with Calabi-Yau threefold, because this is a place where the discussion is general at this moment, but there's some special property about Calabi-Yau threefold.
So there's a relation between different L and the
Yes, if you change different L, it's like change the polarization. So the change of the polarization is a linear transformation which can be generated by coordinate Hamiltonian. So the invariance the change by at classical level is by this Hamiltonian, but at quantum level, this coordinate Hamiltonian give you some kind of Feynman rules.
Well, that's with the high genus. At the moment,
Yes, if you generate everything, yeah. At a level of genus zero, just generated by this basically Hamiltonian flow with respect to the coordinate Hamiltonian. Yes. And also you see, like if you calculate things with respect to 1, it depends on it depends on where you are on the modular space. That's the complex coordinate, and its bar. So if you calculate invariance using this one, you will usually find dependence on tau and tau bar. So depends on this complex structure and its conjugate. This is the conjugate. Yeah. If you calculate things using this splitting, which is a wrong splitting at some point, you will have tau and tau bar things like. Yeah. But I want to mention this Calabi-Yau threefold. So on Calabi-Yau threefold, there's something very special. We actually have a symplectic subspace as follows. So it can pick up, for example, T poly 0, 0, poly 1, 1. This is the only holds for Calabi-Yau threefold. And this space actually is somehow it's a symplectic subspace of the original big space. Because you see the parent like between 1 and t to the minus 1, t to the t paired with t to the minus 2. And under this canonical identification with differential form, and if you read it, you find this is going to be identified with 3-0 form without any t, like 2-1 form, 1-2 form. All the t is cancelled out. This is only true for Calabi-Yau threefold. And so for this on Calabi-Yau threefold, you can, if you use this one as the model of your symplectic structure, as what we did in the beginning, like we write down the period maps for Calabi-Yau threefold, that's basically restricting this period map, the big period map, into this sublocus. And then you find the stuff where you discover from the special geometry on this threefold variation. Okay. Now I want to come to the key point. One of the key points here is the how this story is related to Frobenius manifold. So let me explain the notion of so-called primitive form. This is a notion from Kyoji Saito. And equivalent is same, different notation. J function. This is notation from give and tell. So now let's fix the splitting. So and let's write the basis I just mentioned, like this is BL. That's the cohomology intersect NTL. And this is isomorphic to the cohomology. And now suppose this, let's write this, this is a five-dimensional space at this moment. Now let's write a basis for this one. Let's call this one span phi alpha. So this is a basis. So to illustrate the geometry, I need to introduce one more notion. This is a notion so-called higher residue pairing. Let's define the map K. This is what I promised you last time. This K pairing from this H is my H. Where's my H? H is H is my whole space. It's my pairing on H. It's valued in this Lorentz polynomial. The same formula, but before we study the symplectic structure, we already take a residue for T. But now without doing this residue, you just basically take the trace map. So K alpha Ft beta GT. The definition is a trace alpha beta and Ft G minus T. So without taking the residue. So if you take the residue, you got the symplectic form. I'm going to call this one a higher residue pairing. By the reason I will explain to you when we come to the point on Lagrange model. This is really literally the higher residue pairing in the study of Kyoji Saito. And by this formula, we know like the way this is related to the symplectic form by the following. So originally, we calculate the symplectic form is basically the residue of this higher residue pairing.
This is just descent from Sx, right?
It's defined on the S, and then you can show it descends to the cohomology. Yeah, exactly. So the d bar and this is symmetric antisymmetric in d bar, symmetric in D. So that's why by the set square linear, then it descends to the cohomology. Yeah, you're right. And if you look at this, you modular modulo T as a leading order in T. If modulo everything, this becomes the trace pairing. On the cohomology. Okay. Now, there are some very peculiar properties about this pairing and the splitting. Let me explain what's happening. Okay, so let's try to figure it out. Like suppose we know this H, it can be written as like a H plus of L. So this is my splitting. And because it's like a isotropic splitting, this implies something quite interesting. So first, this isotropic splitting implies that if you look at the pairing between H plus and H plus, it lies in here. If you look at the pairing between the other one, it lies in here. That's why it's an isotropic splitting. So if you take a further ratio, oh sorry, it should be -2. So now this is essentially the same reason as saying that it's isotropic splitting. Basically the same information. But this one says something more. Now let's look at our basis. So our basis is given by this H plus intersect dl. So by combining these two properties, this implies that the higher ratio pairing, if you look at the pairing on this basis, on one side, this is an element of H plus, so it lies on here. On the other hand, it's an element from this side. So if you multiply it by T, it has to be in negative order, non-positive order. So the only possibility is like evaluate there's no dependence on T. It's really, the evaluation is really on the complex number. So this means that if you calculate higher ratio pairing on this basis, there's only classical trace pairing. There's no higher ratio pairing for this object. So let's write this pairing as like a K phi alpha phi beta. So it's a number. Let's call this one eta alpha beta. This is a non-degenerate matrix with no T. No higher T. And for this property, QT Saito introduced a name. Just call this good basis. This choice. A good basis. A good basis is really a choice of the basis where all these higher ratio pairings vanish.
Call it BL.
BL, yeah. Or this choice of, he was using this basis, but this linear space is really the good basis, yes. Okay. Now we need to do a little bit geometry. So this our modular space of here map to let's call this one, this is H plus. Let's denote the projection to be to this basis to be pi plus. So with the choice of this splitting, we can write the projection map. It's a projection associated, which depends on the choice of the splitting. So you really map here, project. And around this origin, like formally, is this diffeomorphism as a formal manifold. Now, and let's see. So under this choice of basis, under this choice of basis. So my space is can be written as the Lorentz series S plus. Again, all this identification depends on the choice of L. And this map is the natural projection under this choice. Project to the non-negative order in T. The next thing we do is to pick up a special deformation as follows. Now consider the following fiber product. As follows. So originally I have the moduli space, and I have a period map to the full space. Now under this composed with the projection map, we map to H plus. And this is formally is a diffeomorphism. Now, H plus is very big. Now I want to specialize to the classical moduli space without descendants. So what you do is the following. You choose, look at the following subspace. Subspace is chosen by this good basis. It's a way to truncate all the higher T's. And now let's look at the fiber. Let's pull back. Let's call this one modular space of something with a knot as a subspace. This is like a diffeomorphism more formally. So let's look at the fiber product. So you can view this one as a special family of the solution parameterized by this object. So here, like, let's write coordinate explicitly. Like this, let's write this coordinate as like a tau alpha k. Let's say k equal to 0. The alpha indicates the choice of the basis here. So I just write this parameterized object by this tau alpha. And this object here is like tau alpha 0, and all the higher t's are vanishing under this choice of good basis. It's isomorphic to the original modular space, yes. With yeah. So it's a special family of the modular space. The special family is the way to indicate, for example.
No, I'm taking the Calabi free and we use the conjugate polarization.
It's bigger than Calabi. Okay, we can restrict the a little bit smaller space. So this includes all the polyvector fields. If you, exactly, yeah. Yes. Now here's the metric. Now comes to my favorite part. So we can identify this data by looking at this. It specify a special choice of the solution. So this identifies a family here. So I could call this one mu. And the solution depends on the choice of splitting. That's called mu L. And I just call this one mu L. And depends on tau naught alpha. And this parameter is the parameter of downstairs. But actually, this is an element of the it's an element of the polyvector field with descendant. And parameterized by this tau alpha. So let me just write it in such a way. This is the parameter.
Again, ML is what is the average zero?
For every point here, so this is my parameter. It corresponds to an object here. So object here is the solution Markov equation. That solution I specify to be this notation. Solving. So it's basically a special family of here. So we solve the Markov equation, and the parameter is the good basis. Now, by the way, this is solution here. This is, if you write down everything, write down this explicitly. I mean, by the construction, you usually have a deep dependence. But the moduli is very depends on this parameter. So the leading terms gives the classical moduli space modulo t, but all the other terms somehow are determined by this choice. So what this one will play the role of so-called primitive form. But let me try to explain what this one precisely means. You have to understand basically this period map. So this one satisfies the following property. It's a solution of the Markov equation, but on the other hand, by this identification, let me probably just write here. So pi plus L composed with T. So what's composed with P? What is P? P is like a map to this object, e to the mu L over T. And look at the Q cohomology. So this means like Q cohomology. And this has the property that only has this component, no higher term. So this two equations captured the special solution. So the first one says like it's a modular space. It's a basis here. I just write a basis. Yeah, it's a basis. So it just means it lies here. So I just use the coordinates right. But this is, if you project, under the period map, it lies literally the leading part. There's no higher term. Yeah. Now these two equations has an extremely special property. My notation here is like Q cohomology. Means Q cohomology. And because you see this solution, same thing saying this is Q closed, and somehow at a cohomology level, this is equal to the basis. Now we're gonna write this equation in a little bit different way. So you see, like this pi.
This is like you start to solving the Markov transform. Probably you have to start with the first order, and then you try to solve the problem.
Yeah, with a special property. Yeah, you solve the higher orders in a special property. Okay. So explicitly, because of the Lagrangian cone, I also tell you like this is a generating function here. Equivalent, you can write like a t 1 minus mu L over t. This depends on tau, 0 alpha. At the cohomology level, another way to write this is the following: like on the positive part, you only have this order, But on the negative part, you have many other stuff. So I want to rewrite a little bit. So another way of writing this equation is the following: like t 1 minus e to the mu l over t at cohomology level, period map, can be written as like this is the positive part, which only start from order 0, no higher order. The negative part is about the generating function. So k from 0 to infinity, minus 1 to the minus k minus 1, t to the minus k minus 1, and eta alpha beta partial. This is a generating function. Tau beta k. And restrict to phi beta. And finally restrict to tau bigger than 0 is 0. This is the other direction, the negative part. This is given by the graph of d something. I just write it out explicitly. That's the d of something. And this is the inverse of the trace pairing that I just write. And FL L better. Yeah. So you see, like this is a if you look at this formula, this is like a one descendant generating function. So what?
So this is a direct. You need a direct implication, right? This is not.
This is by definition. This is like this graph with, because this is the negative part,
Yeah.
and the positive part is only this part. So it's from like t to the order 0 or t to 0. Because this period map, the period is given by the graph of.
The solution.
Yeah.
So
This equals the graph of d f0. And so the negative part is given by the derivative. And so eta alpha beta.
So one descendant comes from because this is graph of the df.
Yeah. One descendant, but different orders in T. Yeah. So I have to order one descendant with different order descendant degrees, and then restrict everything to the ordinary moduli parameter tau, because it was restrict to this particular slice. And so here, and what the meaning for this one is the following: like this component. So you see, like this is a very familiar object. It's one descendant generating function, and which is called by given tail the J function. We're going to call this one tau 0, the J function. The left-hand side, let's rewrite a little bit. So eta alpha beta is the inverse. I just mentioned inverse of. And the left-hand side is basically a period map. So we're going to rewrite this a little bit as saying that this e to the mu L over t at a cohomology level, the same thing as 1 minus t minus 1 j. So this j function and this object will be identified with Kyoji-Saito's primitive form. This is like a primitive form. So this object is a j function. So they're actually the same object, but they're viewed on a different viewpoints. And what's more interesting is the following. Like, this is a notion by Kyoji-Saito. This notion by given tail. the same object. Now, let me erase this part. Now, one of the property that leads to the notion of quantum differential equation is the following. Let's calculate the tangent place of tangent place of this Lagrangian restricted to this primitive period map. So the property is the following. If you calculate a higher residual pairing, like say, take a derivation for J function. It can be done equivalently using primitive form of the same object. So a priori, I mean, this one has many t dependence, but if you take the higher residual pairing, magically, this is only a constant, doesn't depend on t. And this is the most important property. And how this works, this is the art of comparing two sides. And so let's prove it. I mean, this is because it's a crucial property. Let's try to prove it. So by the expression of J, the J function, J is defined here. If you take the derivation with respect to the parameter, you see, like, if you calculate the higher residual pairing of these two, and you'll see, like, if you take the derivation, it becomes, like, say, if you look at the expression, the leading term is the phi alpha plus negative order in t, phi beta plus negative order in t, expressed in terms of the good basis. And then I mentioned, like, if you calculate the pairing between good bases, there's a constant. So the other stuff will be subsquilinear in t. So this object is basically eta alpha beta plus negative orders in t. On the other hand, we can calculate the same object using this relation at the level of cohomology. And on the other hand, if you calculate the same object, because I mentioned, like, this K higher pairing is very defined on the cohomology, you can calculate the same object from this equation, from the left-hand side. And so this is the same thing as calculating the derivative for the other expression for Saito's primitive form. Now, if you look at the variation, and this is actually easy to see, like this is given by, this is constant, and then you find something like a minus, let's forget about the minus sign. So mu L e to the mu L over t partial mu beta and you see, like, this lies in the tangent plane of the module of the Lagrangian cone. And I mentioned this is basically a Lagrangian subspace. Another way of saying this is the following: like, this is only non-negative order in T, and with this conjugation doesn't break down this non-negativity, and we'll find this object in non-negative order in T. This is a non-negative.
Yeah, this is not the other.
Yeah, but this is like mu L is like mu 0 plus t mu1 plus etc. So all this stuff, if you divide by t, is non-negative. This mu0 over t, if you calculate by the formula of Harris pairing, we cancel with this one. But because that's square-linear map, so it's a mu lt, and here's mu lt. We calculate the square-linear map. This one has to multiply by minus t. So when you calculate the Harris pairing, you basically multiply this object with the minus mu, and they cancel out. So the leading term canceled out. All the other stuff are negative, but by the formula of this k. Yeah. So the same thing as saying that, remember we I just leave an exercise to show why this image of the period map is a Lagrangian. The same calculation basically, because this is the tangent, lies in the tangent plane of the period map. So now you compare the left hand side, the calculation from the J function, on the right hand side, the calculation from the primitive form. And the left hand side shows like this constant plus negative order. This has to be non-negative order. So comparing these two sides, you find k equals the only possible non-zero term is this guy, and that's the proof. So what happened? What's really happening is the following. So we still need to draw some picture. So I'm gonna leave. Maybe I can erase this part. So you see, like this one says the following, like. Maybe I can erase everything. I don't need this anymore. So this one implies the following, like this object gives rise to a family of good bases in the sense of QG-Saito. Parameterized by this tau. And actually, this is easy to understand from this geometric point of view. So roughly speaking, geometrically, so what is this guy? I mean, this is span. It's really at this particular, it's really at the point tau. From this calculation, the right-hand side is about, you see, like this is really around the tangent plane of the moduli space. The left-hand side is about the splitting. So it's really the element of the tangent plane at this tau of the moduli space intersect with the splitting of the splitting. So this one says like it's only negative in t, so on this lies here. And the right-hand side tells you like this, you do the variation is on the tangent plane of the moduli space. But this one says the following explicitly. At the original point, when tau equals 0, this intersection is nothing but TTL, the moduli space, intersect with TL. Without any deformation, it's at just a horizontal point. This is really nothing but TH plus intersect TL. That's our original choice of the good basis. And then you let them go, I mean, along this moduli space. And we know at this point we have the splitting. In the beginning, we have the splitting.
You say that you choose a good basis as origin, that we do this good basis everywhere.
No, when the moduli is just a zero.
That's the original choice.
Yeah, our original choice.
Then you get good basis, other basis.
Yeah, the good basis you basically you change the intersection in a way. So that's the original point. Then you see like originally you have a splitting, but if you change a little bit in the formal neighborhood, it's still a splitting. So this one, the tau holds for nearby. And you see, like this calculation, I mean, from this primitive form, and this object lies in the tangent plane. It also lies in L. So what this one says is the following: like this is not only a splitting, but also it's an isotropic splitting because this is Lagrangian. So this is also this is a linear Lagrangian subspace. It's also Lagrangian, and this guy actually forms a basis. That's roughly speaking the idea. And you let it go, it deforms a little bit, but the hierarchical pairing still vanishes because it's still intersection of two object isotropic subspace. Then with this data, we can now discuss how this relates to a so-called quantum differential equation. So the idea is the following: like this is the first order. Then let's calculate the second order. If you calculate the second order, you see like this is linear in tau. That's why it's called flat coordinate. It's important. This is only linear in tau. So if you take the second derivation, this term will vanish. It goes to the next order. So compute the second derivative of the J function. Now we calculate in two ways, either in terms of J function itself or in terms of primitive form. So you calculate directly, and by the expression I just mentioned, the leading term is only linear in tau, so it goes to the next order. It's actually only lies in the negative order in T, which is the element of this splitting by definition, by the expression. Of J. So contains only negative order in T. The leading term is a constant, but it's vanished after you take the second order derivative. The other way, let's calculate this one in terms of primitive form, because they lies in the same converged class. And we can calculate this one by replacing J by this object. And if you calculate this derivation, so this is you apply second order derivation here, you find equals minus, if you take twice derivative, and the leading term is given by, if you apply derivative once, you pull out 1 over t and the other one, so you should get 1 over t derivation of mu L, derivation of mu L, that's the first term, plus the two derivations apply to the same object. Mu L and e to the mu L over t. Two converged class. So that's the second order derivation you calculate. And now you observe, this is a non-negative order. This is a non-negative order because all the mu's have non-negative in t. So this is t 1 over t. So this is means like this lies in 1 over t, the tangent plane of this of the modular space at the top. Because I mentioned this tangent plane is just the negative stuff multiplied by this object. So what this one says, it says something quite remarkable. Yeah, it's here, okay. This one says that if you calculate the second order derivation in terms of this flat coordinate, so this particular coordinate J, it lies in the intersection of 1 over t, the tangent plane, intersect with the L. That's what we find. What do we find? So J is here, and the other one is here, and this is a 1 over t. This tangent plane intersect with TL. However, I just mentioned this one by the calculation of higher superior. This one is the basis of this object. It's spanned by this first order derivation. So this implies the following. So it means like this can be written as a linear combination of the first order derivative. This one is spanned by this implies that there exists a function. Let's call this one A alpha beta gamma tau, such that the second order derivation can be explained. So it's like take a second order derivation J plus 1 over t A alpha beta gamma. That's my linear coefficient. It depends on tau. When the point is moving, this actually the coefficient is also moving. But it can be also uniquely written as a linear combination like that. So this is the peculiar property about the J function. Now, in terms of period map, or this is a way you write J function, but equivalently in terms of period map, this is the same thing as saying that this tau alpha tau beta plus 1 over t A alpha beta gamma tau gamma is operation applied to the primitive form. It's actually 0. This is the same thing. Now, this is a familiar expression for these quantum differential equations. And this object is not hard to show, like by doing a little bit more. This object solves the WDV equation. And the final remark I want to say.
So this is a flat condition, right?
Yes.
So can you say in terms of the journey of the Lagrangian, geometrically, why is that?
Oh, you just like this is Lagrangian cone. This is an explanation by Giventil. You just move a little bit. You move this Lagrangian cone. You roll along this tangent plane. The rolling. It's like order 1, like if Hodge filtration, something like that. That's why you do. Exactly. You specify the order 1 part. It's an exponential map. That's the flat coordinate. And you can show if you lower this index by using this pairing, you can write this one as a like third order derivation of the potential, blah blah. That's simple to show. The calculation is completely same as what we have done for Calabi-Yau threefold example. And so far, this process is pretty actually sort of formal once you have some structures. So if you simply replace everything this polyvector field by, for example, if you twist by superpotential, blah blah blah, you just do the process. You'll find this kind of perturbation formula. It can be calculated like in order by order. For Lambda-Gibbs model that I discovered with Changzhen and Kyoji Saito. I believe Changzhen must have discussed this here. So, but this, in the Lambda-Gibbs case, it's very complete the same. You just do everything complete the same.
The average to compute the A or the average?
Compute just either J, A, or primitive form. This is order by order. Just solve this one order by order, and because this formula behaves like a Birkhoff factorization. So left-hand side is a non-negative, or right-hand side is a negative. You want to decompose in such a way. So once because this whole process works like holds in general. So you can specify this to particular examples. If you do Lambda-Ginsburg, I will say a little bit about it later. Then you got the primitive form, literally the primitive form Kyoji Saito. That's why I call this one primitive form. So maybe I will stop here. So I will continue tomorrow. Okay, thank you.